To continue our discussion of finding maxima and minima from the previous video, I definitely recommend watching that first before coming to this video. But how do we find maxima and minima using first derivative test? As you recall, we can find critical points first by finding the derivative, which is 4x cubed minus 12x squared. For example, the way we define stationary points, we can set it equal to 0 and solve, and in this case we have actually two of them. We could pull out 4x squared and notice how we have x minus 3 left. So if you set them both equal to 0, 4x squared is equal to 0, you can divide by 4, take the square root, you'll still get 0, and then you'll get 3. Again, we do not have any singular points because the derivative is always defined. There is no denominator, there are no radicals, so it would be defined for any x. And there is a single endpoint that we have, which is -1. Infinity does not count as the endpoint. So we'll keep that in mind when we do our test, but we can plot the 3 points that we have, -1, 0, and 3 on the number line, and then it actually continues from there. So -1 is the endpoint. We can just simply plug it in into the factored version of the derivative. If you recall, it was 4x squared times x minus 3. And if we plug in -1, the first part, the square part, is going to make it positive, but x minus 3, -1 minus 3 is negative, so the whole thing would be negative. And so the derivative is decreasing from that point, so we actually have a maximum at that point. So again, refresh that from previous video. You can actually try to fill this in as I'm talking to you guys. Then 0 would give us 0 with the derivative, and because 3 is also a stationary point, we need a point between the two stationary points to determine the sign. We can pick something easy, for example 1 or 2. We can plug in 1 inside of the derivative. Again, let me pause for a second. Here, let me write the derivative using the pen. Let's say f prime of x is equal to 4x squared times x minus 3. In this case, I'm going to talk you through how to find the sign quickly. So if it's 1, again, the first part, the square part, is positive, but then 1 minus 3 would give us negative. Positive times a negative would give us the negative sign. So again, it's decreasing. Now note, there is no sign change. This is the first time when we encounter no extrema. This is not a maximum or a minimum, that it's 0. If you actually look at this graph on a graphing calculator, you'll see that there is a small inflection point at that point, if you zoom in enough, I believe. And then at 3, since it actually continues on to infinity from here, we'll pick a convenient point, let's say 4, to plug in into the derivative, and this time both parts would be positive, so the derivative is positive and the function's increasing. So we do have a minimum at 3, and then we can classify them with the absolute by plugging them in into the original function. So -1, 5, I did not include 0, but you actually would include it on the homework and it would be no extrema at that point. So -1 comma 5 stays as a relative max. Why is it a relative max? Well, because remember how the function goes to infinity. How do we know that the f of x also goes to infinity? So if you recall, the original function was 4x cubed minus 12x squared. That was our derivative. Let me bring up the original function, x to the 4th minus 4x cubed. How do we check what's happening to the function at infinity? Well, always look at the leading term. And since it's positive x to the 4th, it's even power and it's also positive. So what happens as x goes to infinity? Well, your function f of x also goes to infinity. So it's something that's helpful to keep in mind, and because it goes to infinity, then we know there is no absolute max. Let me go back to the original. So we have a relative max, and then 3, -27. This was a single minimum in our function, and since the function does not go to negative infinity, this is actually the lowest y value, and so it would be considered absolute minimum. And that's it for that problem. So one more problem with the polynomials before we get into some other functions. This one has fractions, but do not let that deter you, because when we take the derivative, you'll actually see they disappear. But in this case, we have the open-ended interval. It's from negative infinity to infinity. It's the whole real number line. So how does that affect our endpoints? We'll see. So first, let's find the derivative. So 4 times 1/4, it's actually 1, t cubed. And then 3 times negative 2/3, the 3's will cancel, leaving us with negative 2t squared. And then 2 times a half, that would just be 1t. Set that equal to 0. Note you can pull out a t. So you'll get t squared minus 2t plus 1 equals to 0. And we can factor this. So you can either just break it up, t and t, and then positive 1, you can break it up as negative 1 and negative 1, and they both add up to negative 2, so that works. Or break it up as a square. Either way, it looks like we have two stationary points, t equals 0 and t equals 1. We do not have singular points, again, try to figure out why, and we do not have endpoints. So that's all we have is is stationary points in this case. We can put them on the number line because the 0 and 1 are both stationary. We actually need some extra points on either side to determine the sign of the derivative. So I happen to pick negative 1, again, to plug it back into the derivative. Again, it helps to have the factored derivative version. This is actually g of x, or g of t, sorry. So g prime of t is equal to t times t minus 1 times t minus 1. Or you could have put t minus 1 squared. Same thing. So if we have negative 1, so notice we'll have negative, and then negative, and then negative. So 3 negatives, and so the product would be negative as well. So you can do this. So between 0 and 1, there are no integers, but you can easily pick a decimal. That's 0.5, let's say. And similarly, you can plug it into the derivative. So I'll just do it one more. So 0.5, this time we have positive on the outside, but then we have negative in both parentheses. And so the result is positive because there's even number of negatives. So we have plus, so we do have a relative min at 0. And then on the other side of 1, I picked 2. Again, something easy. 2 would give all three of them positive. So again, the sign does not change around 1. So they're both positive, so there's no extrema. So we only have 0, 0, that is an extrema. And it happens to be absolute min. Why? Again, we have to look at the endpoints. What happens as t goes to negative infinity and positive infinity? If you recall, our interval was both of them. It was the whole number line. Well, because I think we had t to the 4th. Again, you got to look at the leading term. We have 1/4 t to the 4th. So it depends on the sign and the degree. And because the sign is positive and the degree is even, that actually helps with negative infinity especially. Because it's even degree, both negative number and a positive number, no matter how large they are, they would actually give us a positive times positive 1/4 would also be positive. So both ends actually go to positive infinity, as it says right here. So we do have a minimum, but it becomes absolute minimum because it is the lowest point, because both ends actually go up. So there's no absolute max, but there is an absolute min in this case. Okay. Now let's take a look at other functions. So far we've seen polynomials, but this is actually h of x equals x minus 1 to the 2/3 power. This is a radical, the cube root. And we do have the endpoints here, 0 to 2. But it starts out very similarly. Let's find the derivative. We may need to use chain rule, if you recall. So 2/3 comes down. X minus 1 stays, it becomes to negative 1/3 power. Don't forget to multiply it by derivative of the inside, which is 1. And we can rewrite it so that way we don't have a negative exponent. It helps to do it right off the bat in the beginning. So we keep the 2 on the top, and on the bottom we have 3x minus 1 to the positive 1/3 power now. And times 1 didn't really matter, so we omitted it. So Stationary, we can set it equal to 0, very similarly as before. How did I get 2 does not equal to 0? You can always multiply by the denominator. So this is what I did. If you ever have a fraction, you can do that. So times 3 times x minus 1 to the 1/3 power. And because here you can just cancel the denominator, so you get 2. On the other side, you'll still just get 0. Now, of course, this is not true. So 2 does not equal to 0. The top is never 0, so we don't have any stationary points in this case. But we do have singular because note, now we have a denominator in the derivative. So there is a potential for the derivative to have 0 in the denominator and to be undefined. So how do we find where it's undefined? We take the denominator from the derivative, set it equal to 0, and solve for x. And what we would have to check in the end to make sure that the original function is defined at that point. Then we have a singular point. So I just divided by 3, so we get x minus 1 to the 1/3 power equals to 0. Then you can raise both sides to the 3rd power, so we'll get x minus 1 equals to 0. So as you see, we'll get x equals 1. So the derivative is not defined at that point since the denominator is 0, but the original function is defined. If you note, I did not have denominator, it had just x minus 1 to the 2/3 power. So if you plug in 0, you'll just get -1, and you can actually raise it to the 2/3 power. I suggest you try it. So you can find the y value at -1. Sorry, it actually x equals 1, and 1 minus 1 is 0, is 0 to any power is 0. And then we do have endpoints, 0 and 2. So here we have a singular critical point and the 2 endpoints. And again, it works very similarly. And we plot them on the number line with the derivative. We plug in 0 inside of the derivative. And as I have showed in class, you can do similar, let's say you plug in 0 inside of the derivative, you'll get -1 to the 1/3 power is actually still -1 if you think of it as a cube root. So that would give us a negative sign because it's +2 divided by -3. And the function's decreasing, giving us 0 at the endpoint, which is a maximum. And at +2, on the other hand, we'll get 2 minus 1 is +1 to the 1/3 power would give us plus, and it's increasing. So that gives us a minimum at the 1, and it's 2 at the last endpoint as a maximum as well. So again, we find the y values by plugging them back into the original function, and we have the 2 endpoints happen to be absolute max because again, it's the same y value and it's the highest one because the function's actually continuous and on the whole interval. And 1, 0 happens to be absolute minimum. If you draw the graph, it probably looks something like this. And so you'll see the endpoints are actually the 2 maximums, but the minimum at +1 is a sharp point, which is why it's singular. So that's a quick one with a quick example with the radical function for you guys. And here is a rational function, t² + 1 over t² - 1 from -2 to 2. I think this is going to be our last example. Now, with any rational functions, first note vertical asymptotes. It would be helpful when we graph them, and of course they play a role when we find maxima or minima. So they do not form singular points, that's very important, but they do affect sign changes in the derivative, in the first derivative test. So they must be included. So, in order to find stationary, singular, and endpoints, we must take derivative. So make sure to use quotient rule to find the derivative. Hopefully you're getting -4t over t² - 1 squared. And again, you can set it equal to 0 to find stationary points. And again, you can multiply both sides by denominator and clear it. And that's why I get -4t equals to 0. So note, with any rational functions, if it's equal to 0, it really matters what the numerator is doing, as you'll note. So we do have a t in the numerator, so we can divide by -4, so we get t equals 0. So we do get a stationary point in this case. For singular, we can set the denominator equal to 0 and solve for t. But note, once we do solve for t, we'll get positive and -1 again. But remember, those were vertical asymptotes and the original function was not defined at those. So singular points, just like any critical points, give us candidates for maximum or minimum. Obviously, the function at vertical asymptotes is not defined at those points, so it cannot have a maximum or a minimum at those points. So usually with rational functions, asymptotes get preserved throughout the derivatives as the more you take them, but they do not form critical points. However, notice how we do have endpoints, but notice how I included the vertical asymptotes in the first derivative test, because the sign may change on one side of the asymptote. What the function is doing on one side of the asymptote may or may not be, it may be something completely different than on the other side. So typically what I do with rational functions, so we can write them out. Again, I write out the derivative, which was -4t over t squared minus 1 squared, and again we can do a similar sign table. So for example, the endpoints you can plug in. Now this time I plug it in the top and the bottom and check for the signs. So -4 times -2 gives us positive in the numerator, and in the denominator it's square, so it actually would always be positive no matter what. So that's how come we get the sign to be positive. On the other side of -1, which is the vertical asymptote, so again, let's note that they're both vertical asymptotes. It's 0, it's a stationary point, so we need something between the asymptote and the 0. So I picked -0.5 and also 0.5 just to check the signs. Same thing, if you plug in -0.5, you get the top to be positive divided by positive, so the sign is still positive. So if you note, with vertical asymptotes, again, just because the sign didn't change doesn't mean it's the same graph. On one side, the graph could be increasing, for example, if this is our vertical asymptote, and on the other side, it could be increasing. But notice how the two pieces are very different. So one side could be increasing this way and the other one could be increasing this way. So just because it's positive doesn't mean it's the same thing necessarily. And same thing, we can plug in positive 0.5. This time we'll get a negative because the top would be negative. And at 2, we also get negative for the same reason. The top is negative. So we do have a maximum at 0, but we do have 2 minimums at the endpoints based on our first derivative test. And I plug them back into the original, which was t squared plus 1 over t squared minus 1. So if you square the number 4, for example, plus 1 is 5, minus 1 is 3, so we get 5/3. And I had to change the absolutes to relatives. I'm going to explain why in a second. And then 0. This should be 0 should be -1. That's another little typo, so please note that. And then 2 and the 5/3. Now notice something strange happens with rational functions. The y values for the minimums are actually higher than the maximums, and you may think how that could be. So if you draw the graph on your graphing calculator, it could look something like this. So let me redraw it real quick. I had to pause the video to draw the graph, and please forgive any noises in the background. Seems like there's some traffic happening outside of my window. Anyway, here's what the graph looks like. So if you note, at the endpoints, actually I should have stopped at the endpoints, it does not continue. We do have the 2 minimums, so notice that's why they're relative. Because this function is not continuous and it has asymptotes in the interval, notice how there are pieces that are going to infinity and negative infinity, and so we do not have absolute maximum or minimum. But the endpoints are relative minimums just for their pieces, and we have one relative maximum right here, again, just for its piece. So definitely with rational functions, draw the graph, and hopefully it'll make more sense what you have at each point. And that's it for this video.